out. Okay, I think you can read that now. Okay, I tell you what, let's do 1 and 2 first. Go ahead and do 1 and 2. I'll give you a few minutes to do 1 and 2, and then we'll go back and we'll do 3 and 4. So let's start with just the 95% confidence interval. Now, don't type in your answers, but just type in done if you're online and you're done, so I get a rough idea how long it's taking. That's correct, Alicia. You got exactly right. That's why it's a smaller sample size. So the ranges, even though all of the other numbers are the same, the sample size made those confidence intervals wider in every case because the standard error, instead of being 3, was 5. So now when you multiply by 1.96 or 2.58, all the cases, you're always adding a bigger or a bigger number, adding and subtracting a bigger number. In other words, it's a wider margin of error. How you guys doing back there? You guys okay back there? I mean, you're sitting there, we have like 4 people here. You guys are in the back corner of the room there. I know it's a guy thing. I don't know what it is, but I understand. It's okay. I don't mind. You're not hurting my feelings. But I just, every once in a while, I have to check with you guys and see if you're doing okay back there. Dave, how you doing? Okay. Sure.
Clarify. So standard error refers to the error with the sampling distribution, and margin of error is just a specific sample that we take out.
No, standard error represents the standard deviation of all the samples that you might have.
Yeah, that's what I meant.
Right.
Right.
That's a sampling distribution. The margin of error is how much you add and subtract from the mean in order to get the confidence interval. In other words,
that refers to a specific sample.
Yeah, because it's only for that one. It's got to be for that one calculation, confidence interval. Yeah. Okay, I don't see any dones online there. You guys fall asleep back there? Or? Okay, here we go. Thank you, Karen. Okay, I'll wait a little bit longer.
We're gonna go over the homework.
Excuse me?
The homework.
Yeah, I could go through a bit of homework. I'll leave a little bit of time. Okay. Don't forget you can resubmit. In other words, I know almost the people that have already submitted homework 3, right? I'd say about 60% of them just got them all right. 40% of them, 40% got maybe 2 or 3 problems wrong. All the same problems, the last 3, right? And there's a reason for that because I didn't really go over that very much on the last 3. In fact, it may be a little bit clearer now that we've done this. Yeah, the last 2 or 3.
I know. I remember last time.
The proportion, right? And we're going to talk about proportions and how they affect confidence. What's that?
We're just using a formula.
Yeah, exactly. Yeah, exactly. I gave you the formula, right? On the homework, I gave you a formula. But I'll go over it because a lot of people didn't apply it correctly. So I'll go over that. In fact, we're going to talk about proportions where the confidence interval is concerned shortly. Okay, so I'm going to go ahead. I think we're starting to get about half of you guys have done this. So I'm going to go ahead and now we're going to take a look at how we would do this calculation to see if you would do it the same way I do it. Okay, so what do we have here? We have a sample. The sample size is 1,000. The mean is 180, and the standard deviation of the population sigma is 30. And we want to calculate confidence interval. Okay, so let's see. Okay, the mean x bar is equal to 180. Did I say 180? The standard deviation of the population, usually we don't know that. In this case, we do. It's 30, and the sample size is equal to 1,000. We want to calculate a 95% confidence interval. Okay, so let's see what that's going to be. That's going to be equal to x bar plus or minus 1.96, right? So it's going to be 1.96 because it's a 95% confidence interval, times the standard error. A lot of times, you'll see people put into here, instead of 1.96, they'll put z 0.025, right? Well, what does that mean? That means the z-score for a tail of 2.5%. Well, 2.5% of one tail would be added to the 2.5% on the other tail of the distribution. That's 5%. In other words, the z-score that represents 95% of the population, which would be 1.96. So that's why you'll see that. If you see it, don't get confused by it. They're asking you for 1.96. Later on, when we're dealing with small samples, you'll see t 0.025 or 0.025, because you have to use a different distribution for small samples. Don't worry about that for now, though. Let me see if I can't get rid of that. Like, whoops. Okay, get rid of all that nasty stuff there. Go back in time. Okay, so let's see. Let's take a look at this. So what's it going to be? It's 180 plus or minus our margin of error. Our margin of error is going to be equal to 1.96 because we're at 95% confidence interval times the standard error. Well, the standard error is equal to 30 divided by the square root of 1,000. Well, oh no, we got a problem. We got to actually calculate that, and we got to use a calculator to do it. You know, I used to know how to do square.
31.6.
31 point. You remember that, or you just like it?
No,
Okay, good. That's good. You know, at one time I learned a method by hand. You know, like you have to remember, I went to school in prehistoric times. You know, so they taught us a method for calculating square roots. It had something to do with starting from the top end and pairing numbers up, and it was complicated, but there was a method for doing it by hand. I honestly don't remember how we did it, but there was, and it had something to do with pairing up digits starting from the left or right from the decimal point. I don't remember exactly how it worked exactly, but one of these days I'll try and dig that up. But yeah, now we have calculators, so no one has to do any of that stuff anymore. Let me just make sure it's muted here still. Okay, so it's 1.96. Standard error is 30 divided by, and you said again, what was that, 30 over 31.6? What does that come out to? 0.0.
You mean the 1.96?
No, 30 divided by 31.6. How much is that? What's the standard error actually equal to?
30 divided by 31.6 is 0.94.
Okay, good enough. 0.95, let's call it. 0.95. So this would be 0.95, right? Roughly, it looks like 1 times 2. So, I mean, so what does it come out to? 180 plus or minus 1 to give me the actual number that the standard, that this comes out to, which is 3 point,
1.862.
no, it's going to be 3.7. I'm sorry, you're right, 1.862. I'm going to call it 1.86. So this is called our margin of error, right? That's informal. You don't have to know that. I mean, you know, that's what you would call it, because you kind of margin of error. Because I'm saying, well, I think the average weight for the men in this population is 180 plus or minus 1.86. Kind of natural to call that margin of error, right? Could be that much higher, that much lower. So what does that come out to be? Our 95% confidence interval. 178.14 and 181.86. So we're 95% sure that the average weight for all of these people, all these men in DeKalb, a million men in DeKalb County, you want to know something? That's the stupidest problem. It just occurred to me. There's no way in the world there's a million people in DeKalb County, Georgia. Unless it includes Atlanta. I guess if it includes Atlanta, it could be, right? Okay, so at any rate, it's 178 to 180, 182 roughly is going to be our 95% confidence interval. The next question was, I think, to determine the 99% confidence interval, or we change the sample size. What about if the sample size is exactly the same study, with exactly the same mean, exactly the same population, except the sample size is smaller? Let's see how the sample size affects this. Well, now the standard error is equal to 30 over square root of 100, which is 10. It's equal to 3. So now our margin of error, 180, this is for, it's still for 95% confidence interval, right, is 180 plus or minus 1.96, roughly 2, times, instead of 0.95, 3, right? So this is 180 plus or minus, I'm going to round off here for the moment, 6. So our confidence interval now, instead of being 178 to 182, our confidence interval now is 174 to 186, right? See what happened there with that sample size? Because that square root, because that sigma over the square root of n, right? The standard error gets larger as the standard error gets larger as n gets smaller. The standard error gets smaller as n gets bigger because you're dividing by n, right? Inversely proportional. Okay, you guys get that? Are you guys okay with that? Atlanta's in Fulton County, so twice the I was right. There's no way there's a million people in DeKalb County, right? That's probably a pretty rural area. So at any rate, let's move on to I'm gonna skip 99% confidence, and you're gonna do the same thing, except instead of using 1.96, you're gonna use 2.58 for each one of those two problems. So it's gonna be 2.58 times 0.95, and it's gonna be 2.58 times 3 to get your 99% confidence interval. And since it's bigger than 1.96, it means that your margin of error is going to be bigger, which means that your confidence interval is going to be wider for that higher level of confidence at 99%. Okay, so now let's take a look at one that involves a proportion. Okay, so you want to know something? Is that correct? Yeah, I think that's correct. Okay, so a major metropolitan newspaper surveyed a simple random, did a simple random sample of 200 voters. They asked them whether they planned on voting for a new bond act. 55% said they planned to vote yes. What's the 95% confidence interval for the proportion of voters in this population who will vote yes? What's the margin of error for this poll? This is getting interesting because they really use the term margin of error in polling, don't they? Okay, so now let's take a look at this. How are we going to determine this? Well, you want to know something. In this case, we're dealing with a proportion. That's a point estimate, like on mean. No, remember Levi will refer to numbers that represent the middle of a population or distribution as a point estimate. The mean is a point estimate. The percentage of people have diabetes, the prevalence of diabetes, point estimate, 0.125. But the confidence interval is a range. It's not a point, it's a range. Okay, so we're going to calculate the 95% confidence interval. Now, what we're going to do is we're going to use that 55% as our point estimate. We believe that the middle, that the probability a person would vote yes for this bond issue is 0.55, right? A little bit more than 50% chance he's going to vote. But since only a sample of 200 voters, can we be 95% sure that the bond is going to pass? Well, we would be 95% sure if the 95% confidence interval stayed above 50%. If the 95% confidence interval was 45 to 60%, we wouldn't be 95% certain that we would get more than 50% of the people voting for it. Could be we'd get 47 is the real percentage, or 46, or 61, or so on. The range is going to give us what range we should expect to be 95% certain the real percentage of people voting yes would be. So let's give that a try. So I'm going to go back here. I'm going to get some fresh paper. I'm sorry, what's that? On this end, yeah. Okay, I don't know why that keeps popping up. Maybe something I'm doing, a key I'm hitting or something like that. Okay, so let's take a look at this. Let's get this out of the way. Oh, click on that. Let's get that out of the way. Okay, so what is the proportion? Now P represents the proportion of people that are going to vote yes. Okay, I'm going to take a sample from this population. This is what Levi was talking about before. Levi likes to use a big P for the population proportion and a small p for the sample proportion, right? In the book, I think most likely they use a p. P represents the population proportion. P with a little, what is that called, that symbol? Like, they use that in German, right? It's not like an umlaut is like that. It's like a little curve or something like that, and then there's two dots. I think they use a cap like that also. But at any rate, I call that, when I can't write that, I call it P cap. Just like when I can't draw this, I call that X bar. I tend to call that P cap. That's what he was referring to. P cap represents not the population percentage, but the sample percentage. That's the way I just distinguish between them. Just like we distinguish between the means, mu is the population mean, X bar is the sample mean. Okay, so P cap is my sample, my sample proportion. And that's equal to 0.55 in this case. What's our sample size here? It's 200. Okay, so now my standard error for proportions. Okay, and this involves a binomial distribution because a proportion is really a binomial distribution, right? In other words, they vote yes or no. There's only two choices, right? So 55% of the people are voting yes. So that's going to be, my standard error is going to be equal to the square root of, I'm not sure that formula is right. It's P times 1 minus P over N. Is that right? As N gets big. Yeah, that's right. That's going to be right. Okay. Okay, there's another formula, N times P times 1 minus P. And that's only when you're actually counting the number of people that are voting yes. But yeah, this is right. So this is going to be equal to, what's my standard error going to be equal to? It's going to be equal to the, now notice that this P is going to represent a measure of your standard deviation of your population, and it's represented by how many people. In other words, if it's 0.5, standard error is going to be very big because there's a lot of uncertainty. Half the people voting yes, half the people voting no. If we're 0.1, there's less uncertainty. You'll see that the number standard error comes out lower. You don't have to worry about that now. Just worry about the calculation for now. So P is 0.55. We're using P cap as an estimate of what P is, times 1 minus P is 0.45, over my sample size, which is 200, and then the square root of the whole thing. Okay, so what's our standard error come out to be? Anybody want to? Yeah, I'll do that while you're working on it too, so you can check it. Okay, it's going to clear this 0.55 times 0.45 divided by 200 is equal to that. And I got to find the square root of that. Square root of that is 0.035. Okay, 0.035. You guys are, oh, good, Carol, good work. So I'm hoping you guys online, all I did there was multiply 0.55 times 0.45, divide by 200, divide the answer to that by 200, and then take the square root of that. You'll notice that when you take a square root of a fraction, it actually comes out bigger rather than smaller. It came out to be 0.035. So the standard error is 3.5%, 0.035. So now how do I calculate my confidence interval? Well, remember before we calculated by using X bar plus or minus 1.96 times my standard error. Well, in this case, I'm going to use P cap as my starting point, my point estimate, plus or minus 1.96. And now my standard error is going to be this percentage, 0.035. So I'm going to, for the moment, make believe that this is 2 rather than 1.96. So it's going to be P cap plus or minus 2 times 3.5%, plus or minus 0.070, roughly 7%. So let's see. So it's going to be P cap, which is 0.55 plus or minus 0.07. Okay, so now notice this is called my margin of error. So, like in other words, if you saw this in the newspaper, they would say our polling says that this bond is gonna get 55% yes vote, plus or minus a margin of error of 0.07. Literally, that's the way you would see this reported. Okay, so what is our 95% confidence interval? We're 95% certain that the true percentage of people that are going to be voting yes for the entire population is going to be 0.48 to 0.62, comma 0.62. Are we 95% sure that this bond is going to pass? What do you think? What do you guys online think? Are we 95% sure this bond is going to pass? We're not, are we? Because we're not 95% sure that it's not more than 0.50, right? We're 95% sure that it's between 0.48 and 0.62, which means it could still be less than 50% and could fail. So you guys get that? How this confidence interval tells us that, well, we're 95% sure the real percentage of people voting yes is between 0.48 and 0.62. Had this come out to be 0.52 to 0.62, we could have said that we're 95% sure that it's more than 50% because we're sure 95% sure that it's between 52 and 62%. So that's how we can use something like this to understand whether from our sample that this population is different than some other value that we think we want to compare it to. Okay, I see a lot of glazed eyes here,
So if
faces.
it's at 0.52
We-
as the interval, you could be 95% sure.
Exactly, because 50% is outside of the range. We know that all the values below 50% are outside of the range that we're 95% sure the true proportion is. Okay, now let's take a look at another example here. Okay, so now we're going to move on to some real world examples. You know that there's a lot of in public health, there's a lot of underserved populations, right? One of the major underserved populations is zombies, right? Nobody worries about public health of zombies. So we're going to take a look at the public health of zombies. Okay, so the primary food source is brains and spinal cords, so on and so forth. Here's a zombie food pyramid, you know. So you'll notice bones and gristle not sparingly, you know, just cut down on that if you're a zombie. So let's see, the serum cholesterol, we're worried that they have a diet high in protein and low in carbohydrates since they're eating brains most of the time, almost like low carbing. Serum cholesterol levels are measured in 25 randomly selected adult zombies. The mean is found to be mean cholesterol levels 1.150, 1.4. The population standard deviation for zombie cholesterol levels is 38. Okay, calculate the standard errors for zombie cholesterol and calculate a 95% and 99% confidence interval. We're just going to try 95%. Now, I am going to cheat here. Well, hang on a second. I'm not cheating. Remember, I told you that we have to have either a sample size greater than 30. We don't here, do we? Or we have to have the population standard deviation, which we do, right? So that means I can use the z-score. I can use 1.96. I bring this up now because on Wednesday, we're going to be talking about situations where we have small sample sizes and we don't know the population standard deviation. So we're going to be stuck. We got to figure out how we're going to deal with that. Okay. This watch here, every once in a while, it's got this health thing. And every once in a while, it taps me on the wrist and tells me to stand up. Okay. So ironically, so you know, they got this whole GPS thing in this too. You would think that it would know when you're going 60 miles an hour in the car, and then every once in a while, every hour, so you get tapped on the wrist, stand up, right? When you're like flying by an exit or something like that. So the software on this stuff is nice, but it's not really worked out yet. So at any rate, I'm sorry to interrupt you guys. My watch dinged. Okay, so at any rate, so let's take a look at how we would solve this. The only reason we could use the z-score, use 1.96 now, is because we know the population standard deviation. Okay, so let's solve this. The 99% confidence interval for zombie cholesterol. Okay, so let me get this out of the way. Okay, and what did I say was to start the mean? The mean was X bar is 151.4. Sigma is equal to 38, and our sample size is equal to 25. So what's standard error? Standard error is going to be, we can calculate because we know the population standard deviation is going to be 38 divided by square root of 25. It's going to be 5 into 38, which is going to be 7.6. Okay. And what's our 99% confidence, 95% confidence interval going to be? It's going to be 151.4 plus or minus 1.96 times our standard error of 7.6. 7.3? No, 7.6, right? So 3 over, that's 20, that's going to be 5, right? So it's 7, leaves 3, 3 over 5 is 0.6. Okay, okay, so that's going to be equal to 151.4 plus or minus 2 times that, which is roughly 2 times that. I'm going to call that 15, just make things go a little faster here. So our confidence interval is going to be something like 136.4 to, I'm getting help here in the classroom. 166.4, roughly. We rounded this off a little bit. Okay, so that's how you would calculate this. Let's move on to that last problem, and then I'll take a quick look at homework number 3, because I know there's an issue on one of the problems. Okay, now it's going to be a proportion. Based on a careful study in Night of the Living Dead, it appears that zombies are predominantly male college graduates. You can see the professor. That I remember that student distinctly. I was at his graduation. Okay, a random sample of the proportion of male college graduates in general population in the United States is known to be 0.48. In other words, more females than males. They live longer than we do, so there's more of them. I think there are actually more male births than female births, but you tend to outlive us. Is that right? There's more female births. More female births. I don't remember. Then you live longer, so yeah. So at any rate, I guess it was not so surprising that the population would be more female than male. 48% of the population is known to be male. So now you take a random sample of 100 zombies, right? You survey, you watch all the movies on Halloween, you count the zombies, and you find that 58 out of 100 were male college graduates. What is the 95% confidence interval for the true proportion of male zombies in these movies? Okay, so now our point estimate is 58 out of 100, or 0.58. That's our P cap. And we want to compare it to 48% of the population. We want to know if we know enough to say that there's a higher proportion of male zombies than there are males in the general population. Okay, so let's give this a try. Let's see if we can't calculate this. Okay, so let's see what we got here. So P cap is equal to 0.58, right? So our sample size is equal to 100. Let's calculate our standard error. Our standard error is going to be equal to the square root of P times 1 minus P over N. And we're going to use we're going to substitute 0.58 for P here. I'm going to tell you a secret in a second about this. So that's going to be equal to square root of 0.58 times 0.42 over 100. Okay, anybody? Let's do this calculation quickly. Okay, I'm going to clear it. 0.58 times 0.42 divided by 100 and equals this, and then I'm going to take the square root of this, and it comes out to be about 5%. Okay, so the standard error is equal to 5%, 0.05. Okay, 0.05. So now let's calculate my confidence interval. Well, it's going to be equal to 0.58, right, our P cap, plus or minus 1.96 times the standard error. Okay, it's going to be 0.58 plus or minus 1.96 times 0.05, right? 2 times this is about 10%. So my confidence interval is going to be about 0.48 to about 0.66.